Welcome back to LabRat Scientific. Now today I want to talk about heat and heat transfer. Now before we get started, let's try to understand a little bit about what heat is. Now prior to the 19th century, scientists thought that heat was actually a physical substance. And that substance was known as caloric. And the more caloric an object had, the higher its temperature. Now today we understand that the heat is not a physical substance, but it's actually energy. And that energy can be transferred from one object to another, and that's known as heat transfer. Now there are three ways that heat can be transferred from one object to another. One is radiation, another is convection, and a third is conduction. Now what I want to do today is show you a few experiments that demonstrate these various concepts. Now the first heat transfer concept I want to talk about is convection. Well, what do I mean by convection? Well, that's when a fluid, such as air, is heated by some sort of heat source, and as it's heated, it becomes less dense. And when it becomes less dense, it becomes buoyant and will want to rise. Now in that case, what happens is that leaves a void where that air used to be, and cold air comes in behind it to fill that void, and it in turn becomes heated, and it also rises. So if I have this system contained in a box, for example, I'll get the circulation created inside. As the air rises, it cools and then drops back down and then gets reheated. So that is the convection currents that are set up. Now, most every household has a convection device within it, and that's known as your convection oven. It's an electric oven. It heats the air inside the oven, and that circulation sets up so it cooks your food evenly. Now let's look at an experiment to test the idea of convection. Now here's my simple experimental setup. I have an incandescent light bulb, which you know is the older light bulbs, and they generate a lot of heat when they produce light. And I can turn on that light bulb and start producing heat. I've also got a gallon jug here that I put two rubber hoses through holes in the cap. I'm going to fill this jug with fog from a fog machine. And if I blow into the container, I can get a nice stream of fog to come out at low velocity, and I can apply it around the light bulb and see what happens to see if we can set up convection currents around the light bulb due to the heat that's generated. Now here's an image of me filling my plastic container with fog from my theatrical fog machine. Now let's apply that fog to the base of a hot light bulb to see what the convection current looks like. So here's my hot light bulb. You notice the fog is moving upwards. So that means the air is being heated by the light bulb, becoming less dense and then rising. You should notice there's not a whole lot of lateral motion to the fog. So that means the convection current is primarily going straight up in this case, and not spreading out around the light bulb itself. Here's a simple graphic showing what's going on. Here's my hot light bulb, and the red arrows depict the warm air being generated by the heating of the light bulb. Now that warm air becomes less dense and rises, and creates a void at the base of the light bulb. Now cooler air is sucked into that area and in turn becomes heat itself. Now, if I put the system in a container, such as this green box, I can create a convection current much like that in an oven. The hot air rises, hits the top of the container, cools, and then descends around the outside, and then is sucked back into the base of the light bulb where it's reheated and reascends and creates this convection current. Now let's talk about thermal conduction. What exactly do I mean by thermal conduction? Well, that's when heat moves along a physical object, such as a metal rod. Now what's happening is each molecule or set of molecules of that aluminum rod are getting heated up by some heat source, and then they ultimately pass on heat to the adjacent molecules, and those molecules pass on heat to the next molecules until the heat slowly moves down the physical object. Here's a simple graphic showing that concept. Now here's my aluminum bar, and the blue circles represent aluminum atoms. Now when I apply my heat source, some of the atoms above the flame begin to warm up, and I represent that with the red circles. Now heat moves from a hot source to a cold source, so the heat will move down the bar. Warm molecules and warm atoms will heat up the atoms next to it. And so the heating moves towards the right on the bar, from a hot source to a cool source. Now at some point when I move the heat, the system will now begin to radiate heat and begin to cool. And also convection currents will set up, which will pull heat away from the bar. So the atoms become cooler, but you notice that the right-hand side of the bar is still very cold relative to the warm side on the left. And so heat will continue to move towards the right on the bar, as depicted by my pink circles. But overall, the temperature of the bar on the left decreases due to cooling effects. The heat continues to move to the right until the temperature becomes cool enough to where heat flow no longer exists. And eventually, the bar will equilibrate to the ambient air temperature around it. Now let's take a look at an actual experiment that I conducted to investigate the concept of heat conduction. Here's my conduction experiment setup. I've got a hot plate here, which I'm using as my heat source, so I can be very careful so I don't burn myself. I've got a thin aluminum bar, which is my sample, and I've got my two thermistors attached to the bar at two different positions. What's happening here is the hot plate is now on full blast. The coils are getting hot, it's heating up the bar, and heat is transmitting along the aluminum bar or conducting along it. And I can look at the data over here on the computer and see what the temperature is of the plate over time. And I can see that the thermistors were initially equilibrating to the slightly cooler aluminum bar. Now the temperature is increasing. On the first thermistor, it's currently about 85 degrees, to where the cooler thermistor a little bit further out is at about 75 degrees. Here's a screenshot of the temperature of the plate as heating up. The red line, we're currently at 115 degrees Fahrenheit, is the thermistor closest to the hot plate. And the green line is currently at about 87 degrees Fahrenheit, and it's the thermistor that's a little bit further out. Now here's a little bit of time after I've turned off the heat plate. So you can see the temperature of the inboard thermistor is decreasing because the aluminum bar is starting to cool. Now you see the outboard thermistor has plateaued, and it too will begin to start cooling here as the bar cools off and radiates heat away from itself. So the inboard thermistor is currently at 166 degrees Fahrenheit, and the outboard is at 140 degrees Fahrenheit. Here's the data from that experiment. You'll see the inboard thermistor, the one closest to the hot plate, is here depicted in blue, and the orange depicts the outboard thermistor, which is further away from the hot plate. Now you notice that the temperature of the inboard one rises quicker, and there's a lag of temperature on the outboard thermistor. Now here's roughly where I turned on the hot plate, and here's where I turned off the hot plate, and you can see the bar beginning to cool after that. The third heat transfer concept I want to experiment with is thermal radiation. But what is that? Well, every hot object radiates in the electromagnetic spectrum. Now, the hotter the object is, the higher the radiation emissions. Now, not all materials radiate or absorb that thermal energy at same rates. For example, wood tends to be a poor radiator or absorber, where metal tends to radiate well or absorb heat well. Now, let's do a simple experiment to get an idea of how this thermal radiation works. Now, here's the experimental setup to do some tests on thermal radiation. Now, what I have is my incandescent light bulb serving as my heat source. You can see if I turn it on, I produce light and heat. I've got two experimental plates, both the same thickness, same material, and same dimensions, one painted white and one painted black. Well, I want to see which one will absorb or reflect heat better. Now, I've got a little electronic measuring device. In the back of each of these plates, I have a thermistor attached. So I can actually measure the temperature of the plate as a function of time and display it on a computer, and then analyze that data. Now again, when I turn on the light bulb, things start heating up, and I can measure the temperature every minute or so and see how the temperature of the plates progress over time. Now here's my setup once again. I have my test plates here, one black and one white, and my heat source, which is my incandescent light bulb, and the temperature is feeding in the computer so I can look at it as a function of time. Now it's important in this experiment to have the plates equidistant from the light bulb, so they're receiving the same amount of thermal radiation. Now as the light bulb heats up, it radiates against the white plate, and it radiates against the black plate. What we want to do is see if the temperatures of these plates are the same. Now here's a real-time look at the data over time. You can see how one plate heats up actually more than the other, so that's quite interesting. Now here's a plot of the actual test data. What I have is the orange data line is the black plate, and the blue data line is the white plate. So obviously, what's happening here is the black plate is achieving a higher temperature. That means it must be absorbing more of the thermal radiation. You'll see that the slope of the black plate data line is actually higher than the slope of the white plate. So that means it's absorbing energy at a higher rate. Now, roughly here is where I turn off the light bulb so the plates begin to cool. So here's the black plate cooling, and the slope is greater than that of the white plate. So the cooling rate is higher for the black plate. But eventually, they come down to roughly the same temperature, and that's the ambient temperature of the air in the lab. So the question is, why is the black plate cooling faster? Is it because it's the black color, or is it because of the higher temperature? Now I can set up another experiment to test this concept to see why the black plate is cooling at a faster rate than the white plate. Now in this experiment, I'm going to heat up two metal plates in a toaster oven and bring them to the same temperature. One plate's going to be white and one plate's going to be black. I'm going to remove those from the oven, set them apart, and let them cool in the air. So certainly they'll be radiating heat, and there'll also be convection current set up that will cool those plates. And we'll see if the black plate cools faster than the white plate, or vice versa, or see if they cool at the same rates. Here's my experimental setup. There's my toaster oven for heating the plates, my data acquisition system, and the two test plates, one being black and one being white, having the same dimensions and the same material as before. Here's my toaster oven with the two plates inside. Now I brought the temperature of the plates up to about 150 degrees or so. Now it's not horribly hot, but hot enough to maybe burn you if you pick up the metal plates. So you gotta be very careful when doing an experiment like this. Now here's the data from the experiment. You'll see the initial temperature of the plates when I removed them from the oven. Again, about 150, 155 degrees Fahrenheit. You notice the cooling rates for both plates, one black and one white, are essentially the same. The slope of the orange line is the same as the slope of the blue line. That means they're cooling at the same rate. So it appears that it doesn't matter whether the plate is black or white. Now, actually, cooling rate is a function of the difference between the test article temperature and the surrounding atmospheric temperature. So the hotter the plate relative to the ambient temperature, the higher the cooling rate. So that's why the black plate was cooling quicker than the white plate in the previous experiment, because the black plate was at a higher temperature when cooling began. Now, there is probably some correlation between color and radiation, but that effect is relatively small or relative to the temperature differential between the test article and the ambient temperature. Well, that completes this set of experiments on heat transfer. Now you can recreate these experiments using simple thermometers or devices you can buy at a hardware store such as a thermal gun to make measurements of the temperatures. You'll just have to record them manually. Well, I hope you got a little more appreciation of heat and heat transfer, and maybe you'll try some of these experiments on your own at home. Now be very careful when using heat sources. You don't want to get burned, so you should have some supervision or certainly do things safely. And you can always find more information on this topic and others at LabRatScientific.com. I hope to see you next time.